Welcome to Spring LIB.
Let's start this question by drawing out what an FCC cell looks like. So, for an FCC, from one face, it's going to look like this, where we have one cell in the center, one atom in the center of the edge, and one in each corner. Now, this is not to scale by any means, but it gives us the information we need to know, which is that these atoms line up right along this axis right here. And if we count it up, there's exactly 1, 2, 3, 4 radiuses, because remember that if we split this atom in half, it has 2 radiuses, one on each half, as this hypotenuse, which is going to give us the edge of the cell. And this is important because we need to know the volume of our cell. So the volume of our cell is going to be equal to the length of our edge cubed. But we need to know what this edge is in terms of our atomic radius to be able to do anything with it. So let's go ahead and figure that out. So from this hypotenuse here, we can say that we have 4r squared is going to be equal to one edge here squared plus one edge here squared, which is just 2 edges squared. So we can therefore say that one edge equals 4r over square root of 2. And if we clear the fraction, that's equal to root 2 times 2r. Okay, so now we know that the volume of our cell is going to be equal to 8 square root 8 r cubed. If we go ahead and do a substitution of this and cube it all, 2 cubed is 8, and then we have an r cubed left over, so the volume of our cell is 8 root 8. And let's go ahead and run this math using our given radius, which is 191 picometers. So V cell equals 8 root 8, 191 picometers cubed. And that is equal to 1.5766 times 10 to the 8 picometers cubed per cell, because this is a single cell that we are considering. Now let's move along and consider the density that we're working with in terms of atoms. So to figure this out, our density, atomic, not cellular, just the atomic density, is going to be equal to, well, the molar mass, which is 39.948 grams per mole, times 1 mole per Avogadro's number, which is 6.022 times 10 to the 23 atoms. And that gets us a very large number for our density, which is 6.634 times 10 to the negative 23 grams per atom. Now let's figure out our cellular density, or D cell, which is going to be the grams we have per cell. So that's just going to be our atomic density times the number of atoms we have per cell, which we know for a fact in an FCC cell is going to be 4, because we have one on this face, one on the opposite face, one on this face, one on this face, one on the top face, and one on the top face, and each of those are all 1/2. So that gets us a total of 6 times 1/2, plus we have 8 corner pieces, 8 corners on our cube, and each corner has 1/8 of a cell, which equals 4 atoms total in an FCC cell. So we know that we have 4 atoms per cell in that multiplication. And if we multiply 6.634 times 10 to the negative 23, we get an astonishingly large number, which should come as no surprise, which is 2.65 times 10 to the negative 22 grams per cell. Okay, now lastly, we can figure out our density, not in terms of cell, but in terms of meters, because we do know the dimensions of the cell, as we had previously calculated. So let's go ahead and take the density of our cell and divide it by the volume of our cell. So we're going to have 2.65 times 10 to the negative 22 grams per cell, and we will divide that by 1.577 times 10 to the 8 picometers cubed per cell. But we need to get this into centimeters, not picometers, because that's a much more convenient and common way of reporting density. So if we look up a conversion from picometers cubed to centimeters cubed, we see that it's going to be times 10 to the negative 30 centimeters cubed per cell. Okay, go ahead and run that calculation, and we get a final number of 1.69 grams per centimeter cubed.